Good afternoon. I'm Lily from Singapore Water Association. Thank you for attending today's webinar on Storming Innovation with SimTech, co-organized by Singapore Water Association and SimTech Agency for Science, Technology and Research. Before we proceed, I would like to touch on some housekeeping rules and disclaimer clauses. To ensure better connectivity, please mute your microphone and turn off your camera. You may communicate with us after the event. Please share your questions in Q&A icon right bottom, where we will try to provide answers where possible in each segment. Do identify yourself so that we can respond to any unanswered questions. We'll be recording this session and reserve the right to the video. Please complete a 1-minute poll survey at the end of the session. We will forward the recording and presentation deck to the respondent. All information shared is for general information only and does not contain or convey any legal advice or administrative assistance. Information shared today is true and accurate as of publication date. The organizer and the speaker reserve all rights in the provided materials. We'll be recording this webinar on the online video platform. It will be shared and kept for as long as it serves a business purpose for the association. By attending this webinar, you are giving your consent to this recording. Without further ado, may I invite Dr. DONG Xue Cheng, Senior Scientist 1, Sustainability and Life Cycle Engineering Group, to speak on advanced ceramic membrane in nanofiltration. Dr. Dong, please.
Thank you, Lily. Let me full screen my presentation. Can you see the slide full screen? Thank you. So I will give a introductory presentation of our ceramic membrane technology, particularly designed for nano and sub-nano filtration. So in general, when we talk about the membrane technology, it refers to different characteristic separation processes at a different size, different dimension. And it covers from microfiltration, ultrafiltration, nanofiltration, and the reverse osmosis. If we only zoom into the smallest size, which is nano and the reverse osmosis, in this slide, I give 4 exemplary and commercial available solutions in this particular range of the filtration size. So number 1, we have polymeric nanofiltration material and reverse osmosis membrane. So these are very typical technology in the water treatment area. And usually you can see a hollow fiber structure as well as a sheet form of the reverse osmosis membrane material. The second bullet point is a new technology. People also introduce ceramic crystals because of the laminar structure. It provides a consistent permeation size in the nano and the sub-nano scale. So ceramic membrane and the ceramic in the polymer matrix, usually people refer to a mixed matrix membrane. So this is a second option if you consider a smallest size, say nano and the sub-nano area. NAA zeolite membrane is a pure ceramic membrane without any polymer matrix. Pure NAA zeolite membrane is hydrophobic, and it can permeate water and reject all the solvent and low polarity molecules. So NAA membrane is the only one pure ceramic membrane technology that can be applied to the smallest size range. HPLC is another technology which requires extreme high pressure to permeate liquids, and during the permeation processes, molecules with different size, they have different permeation rate, and then at the output, you can consider different time frame to collect the different molecules. So these are a brief introduction of the membrane technology at the smallest size. So in SimTech, we developed a new series of ceramic membrane technologies, particularly for nano and sub-nano filtration. So this membrane, we incorporate crystal technology with angstrom level of filtration size. This is quite comparable to the current reverse osmosis. And because of the nature doesn't have any polymeric material, so this is pure ceramic membrane can be regenerated in thermal treatment. And this is considered as a renewable membrane material. And the nature of it also is resistant to solvent media. So it has a very strong stability in the solvent filtration, and it can be applied to recover high-value solvents, let's say ethanol, IPA, and other organic material from water and solvent streams. So this would be a meaningful and very impactful technology for closed-loop sustainable manufacturing. So this is a graphical illustration of what SimTech ceramic membrane for nano and sub-nano means. We refer to the chart on the left side. Let me use my laser point here. We consider two liquid streams. One is solvent, one is water. So this light blue refers to polymeric material technology, and this blue refers to ceramic membrane technology. Current ceramic membrane, they can handle solvent, but the size is limited to above nano filtration. So if we talk about some comparable membrane can achieve even smaller size, let's say sub-nano all the way to angstrom level. This is what we are doing. And these are the table of different pressure requirements. You can also see that if we consider ceramic membrane, the requirement on permeation pressure is significantly lower than the polymeric membrane material. So this basically illustrates what we are doing and what's the advantage of our ceramic membrane at the nano, sub-nano size over the commercial ceramic and the commercial polymeric options. We started this research track a few years ago, and these are the guiding principles collected and converged from our company visit. So on the left side, you can see some of the key concerns from the industry. Basically, if companies are looking at sustainable green solutions in their manufacturing, the recovery unit usually are energy intensive. Incineration, distillation, and other permeation processes require either a high thermal energy as well as a permeation pressure. The treatment also a batch by batch process, as well as they are designed to be maintained an offline kind of practice. Cost investment is also high, as well as the treatment involves the temperature and other extreme conditions may involve some chemical reactions if the waste stream contains some sensitive ingredients and a sensitive solute that would cause some health concern and operation concerns. Overall, people are looking at carbon reduction. So a new solution, if it has a great impact on CO2 emission reduction, that would be an ideal consideration for the company. So there are yield concern, operation concern, safety concern, cost concern. And based on these four gaps, we revisit the distillation technology, incineration, and we design our new membrane approach in this kind of layout. So our technology value proposition is the material has to be durable. We consider ceramic. And the material has to be compatible with solvent. We also consider ceramic. And the technology after integration has to be monitored online and with better connectivity to a further life cycle assessment to give a quantitative measure of carbon reduction contribution. So this is second key points in our technology. And it has to be able to be modular and flexible for system integration as well as performance configuration. And we also demonstrate our performance in a per-evaporation setup. And the per-evaporation would require less temperature and as compared to distillation. So later I will have some performance data using a evaporation setup. So let me go through briefly our membrane design. So our membrane is not a ceramic in a polymer matrix. It's a pure ceramic membrane. So we use commercial ceramic membrane support with or without surface modification. And we can also do our own surface modification to make sure our crystal material and the commercial ceramic are compatible. And eventually, we will do a secondary growth to merge all the crystals together and form a continuous layer. So all the liquid permeation would go through the crystal design, the designed crystal permeate pore size, rather than go through all the defect, gaps, and other macro porosity. So this is the approach why this membrane only provides a very consistent sub-nano permeation size. So these are the crystals. And after the second growth on the membrane surface, this is a SEM of the continuous surface. It doesn't have any defect. The permeation only occurs through this crystal intrinsic pore size. And this is a picture of all the different variation of our ceramic membrane product. And eventually we designed this module to conduct cross-flow filtration process. Let's talk about the performance. We have membranes for water. We have membranes for solvent. In general, we have two categories of our membrane technology. One is hydrophilic, one is hydrophobic. To illustrate the powerful performance of our membrane technology, we use hydrophilic membrane and hydrophobic membrane for solvent media filtration. Because solvent media filtration, you have different molecule size, and all these are very similar to each other, and also similar evaporation point, and how we differentiate them. This is the number one example. We talk about ethanol and IPA mix, and we put a very extreme condition that the ethanol content is only 5%, and the majority of the liquid is IPA. Then we challenge our membrane, is it so selective in the way that it only permeates ethanol and reject the IPA? So we test the performance in a evaporation setup and quantify the permeate concentration. So the ethanol concentration is shifted from the original 5% to 91%, and the residual IPA is only 9%. So that indicates our membrane has a great selectivity to ethanol. And keep in mind that IPA has a larger molecule scale, molecule weight. However, they are still very similar to each other. And that means this membrane has a very good consistency in the pore size design. And we further test the permeation rate for pure ethanol. This is the permeation rate, about 1 liter per meter square per hour. And we also tested in the IPA permeation. Basically, this membrane rejects all the IPA molecules. So the resolution is great here. And the second case is to further challenge how we permeate a smaller molecule from a bigger molecule from a smaller molecule. So butyl acetate versus IMBK. 5% of butyl acetate, 95% of IMBK. So after this permeation test, the butyl acetate concentration goes up to 70%, and IMBK residue is going down to 30%. The resolution is also there, and this is the permeation rate. We tested the pure butyl acetate permeation rate, almost 700 gram per meter, and this is the performance of how it rejects IMBK. So these are the crystal size of the seed, and after the secondary growth, this is the surface appearance of the membrane. It's a very continuous layer without any defect and the large pore or gaps. And this is one of the summary slides of all the 4 typical membrane products we have. For water, these are the permeability, ethanol, IPA, butyl acetate. This is a class of hydrophobic membrane. So you can see all the water is almost rejected here, although water has the smallest molecule, but this membrane are still successful in terms of selecting or prefer the polymer or solvent media. And this is our evaporation setup, and these are all the membrane product we have. And the second portion, we calculate the energy comparison. Commercial distillation column absorption, we refer to the data from some available database. And we also tested and measured our energy consumption and converted them to the same unit. So in our process, our membrane separation has a significant low in terms of heat energy requirement and the processing pressure. Another example, we tested how to permeate or how to concentrate ethanol from a 50-50 ethanol water system. So this is the traditional distillation process, and this is the energy level of the distillation column. And this is our permeation evaporation setup. So the energy reduction is also very significant. So this would be a summary slide of our membrane technology. We consider all the commercial ceramic membrane, and we did further surface modification. And if we consider our unique crystal technology and we merge everything together, form a continuous layer, we can even provide a sub-nano, say, angstrom level ceramic membrane. These are a few pictures of the surface. And we further extend our technology to module design and preparation system integration. And we can conduct a pilot test and a pilot setup customization. And these are the illustration of our approach. So we're talking about the size at nano and below nano. So this is the range. So this is the mechanism, smaller molecule or hydrophobic molecule. Let's say if the membrane is hydrophobic, can permeate. If the membrane is hydrophilic, water can permeate. This is the product, this is the surface. So these are the modules we have, and this is the permeation setup. Last but not least, we also open our collaboration to all the industry partners and explore for new innovation opportunities. And here we list a few possible areas for further collaboration. Number one is manufacturing sustainability, and say closed loop manufacturing or solvent recovery, water recovery. For example, in the semiconductor industry, there's the IPA wastewater. So can we convert this process into a closed loop manufacturing process by recovering the high value IPA from the waste streams? The second area we can consider is the emerging and the green applications in pharmaceutical, in cosmetic, and in other bio-derived or food and beverage industry. There are many essential ingredients to be extracted. Current process is very solvent intensive. And if we consider this membrane technology to close the solvent loop, that would be ideal for a green and a sustainable new application. And number three, we are also open our collaboration to all membrane manufacturer, system integrator, as well as solution providers to extend this technology to an end-to-end solution for the end user application. So with this, I finish my presentation. Thank you very much.
Thank you, Dr. Don. Now may I have now may we have Ms. Cadence, Research Engineer, Sustainability and Life Cycle Engineering Group, to speak on self-assessment for sustainability excellence in water management. Ms. Cadence, please. Over to you.
Hi. So I will start sharing my screen.
Yep.
So today I'm talking about an excellence framework for helping manufacturing become more sustainable. And the overall program that we are calling it is actually the Green Compass. So this is a joint project that we are working on together with JTC and TÜV. And currently we are in the phase of development, and we are very happy to get any collaborators who are able to try this out and validate it together with us. So the Green Compass is actually a framework that is helping companies and businesses in Singapore to become more sustainable. And we find that there's a lack of some of these road mapping or assessment framework that are very specific for companies to test out and to assess themselves. And we see that there are increasing requirements for companies to do so. So firstly, there are increasing regulations that make sustainability more necessary, whether it's on a government level or globally. There's also a goal to reduce carbon emissions. But we also see that a lot of companies are going beyond what regulation require and have the intention to follow a sustainability trend for their own companies as well as their own customers. So the Green Compass is actually a full framework that considers assessing the company as a basic level, how sustainable are they in different aspects. We recommend that companies to also be to learn about sustainability so that they can start with their own sustainable journey. There could be some labeling and reporting that might be useful for them along the way, as well as we are able to benchmark companies against some of the best in class to identify technologies that they can adopt for improvement. So for the Green Compass, we take a value chain and life cycle perspective to look at sustainability. And the idea is through this value chain and life cycle perspective, companies can gradually transition towards becoming more environmentally friendly, more sustainable, and move in the direction of circular economy. And this, we look at operations that's within company, a product life cycle and supply network perspective, and the key areas we are interested in are carbon, energy, water, material, and waste. And the overview for this is to use qualitative means to assess companies so that they can see qualitatively how they are performing, but also link this to very quantitative measures so that they can implement some technologies, have some tangible improvements, and come back to see how certain improvement activities has helped them. So the areas that we look at within operations would be, as described, energy, water, material, and carbon. But then we also want to encourage companies to look along their whole supply chain and product life cycle to identify aspects of environmental impacts that are very crucial to their operations, as well as impacting the country which is providing the raw material or even where the customers are using their product. So today I will go more specifically into water management and operation. So in this area, we consider all the water-related processes within a facility, as well as encouraging companies to look at what are some of the improvement in terms of water consumption efficiency that they can work on. So within water management and operations, we focus on areas that are key to driving water management improvement in the organization. So this can be from a policy perspective. What are some of the policies that around water management that the company has adopted? What is the level of knowledge for water management within the organization, as well as what are some of the targets for improvement in the organization in terms of water efficiency. We also encourage companies to look at the information system to know what are the type of water data that's currently collected, to what level of detail or how frequent is the water data collected. So this helps the company understand what is the water flow, water balance in the company, and potentially identify some of the hotspots for improvement. We are concerned about how the water data that has been collected is processed and what is it used for, and also understand the actual quantitative consumption and break down the different areas in the company. Lastly, for activities, it's also important that after the company identifies the total water consumption or hotspots in the area, what are some of the technology or projects that has been implemented before so that we can improve water management and reduce water consumption. So we have in the self-assessment, in the assessment that we have developed under the Green Compass, we look at these several aspects to determine the base state of water management in a company and also try to collect some data about water consumption. And this data would be useful in the future when perhaps technology has been implemented for improvement. We can come back to the past data to see what are the impacts due to the implemented technology, what are the improvements due to the technologies that has been implemented. So this is what the assessment looks like. It's in a maturity model form. So firstly, we have some basic qualitative questions about the company. And the first row you look at is about management responsibility. Who is managing the water requirements for the company? And then the person who is answering this question or doing this assessment can read across the different levels and identify what level of description is the most suitable. So this helps us have a basic understanding of what the company level of maturity is in terms of water management. And we have graded this in a maturity progression. So going up towards the right, you move from initial, which is level 0, towards visionary. And the description for the companies would be more stringent the higher you go. And the benefit for this would be if the company sees that they are level 2 right now and they want to achieve better water management, there's some idea on what some of the improvement steps could be as they gradually progress towards becoming more outstanding or visionary. So the Green Compass is actually a full journey for companies, and what I've shared with you is the first step, which is to assess, having a basic understanding and assessment for the company. And within here, we do recommend also that companies would learn about sustainability as well as water management practices, collect the relevant data, and compute some of the key KPIs. After learning and assessing, they can choose to verify with third party to see whether some of the data that they have collected is valid and that stands up to scrutiny. And after that, they can identify key areas, hotspots to prioritize for improvement, as well as plan their roadmap, whether it's a short-term, medium-term, or long-term sustainability plan for water management. So this can be planned through our Green Compass journey. So right after the whole plan has been developed, there can be a process to identify suitable technologies. For example, what Dr. Dong shared just now, potentially some specific technology that can provide some tangible improvements should be implemented to improve the overall water management across the facility or even in terms of product management. So the Green Compass emphasizes the first 3 phases, and we can link companies towards potential technologies for implementation as well. So within the first step where we learn and access, we are in the midst of developing an online version of a self-assessment where companies can quite easily and for free assess their state of sustainability. And we will also provide some basic results in similar to the top right-hand corner, where you can just very briefly see a summarized version of the results of the assessment. We do recommend that you couple this with some learnings about sustainability or water management so that you can identify the most suitable area for improvement. So next, there can be a step for verification if it's necessary for third-party assessors to verify the data that has been collected. Then the third step would be to prioritize based on whether is it the policy information system or activities that are not doing so well. Perhaps you want to prioritize that for improvement and plan for longer term sustainability journey for the company. So the last step, which is implementation, will be to employ some potential technologies to reduce resource consumption. So this could be to improve your data visualization for your shop floor by understanding better how water flows and potentially where are some of the areas for improvement for water recycling or water consumption. So these are some examples of technologies that SimTech has in terms of resource management as well as water and energy management. So this is the end of my presentation. I'm very happy to have shared about the Green Compass in the area of water management. Thank you.
Thank you, Ms. Kaden. May we have Dr. Weiyi, Scientist 2, Sustainability and Life Cycle Engineering Group, to speak on hybrid multi-physics approach in wastewater treatment. Dr. Wu, please.
Thanks, Lily. Let me share my full screen. Okay, so I hope everyone can see my full screen. Very good afternoon. I am Weiyi, research scientist from SimTech. I would like to share the topic hybrid multi-physics approach in wastewater treatment. Let's start with the chemicals for water and wastewater treatment industry. As we know, chemical usage is very important for water and wastewater treatment industry. Various types of chemicals are adopted in a lot of techniques and processes such as coagulation, flocculation, filtration, disinfection, pH correction, and so on. According to Frost and the Civilian reports, the total revenue of this market is about $35 billion in 2018, and the expected annual growth rate is about 5.8%. And as we are pursuing the secure economy and sustainability, the chemical consumption, there's a demand to reduce the chemical consumption associated with wastewater treatment industry. And there are three reasons for this. Firstly, the chemical cost could be account for a high level for water production, and also some of the chemicals, they are very corrosive and require harsh storage conditions. And secondly, the process of chemical production is not sustainable. And thirdly, some of the chemical input could lead to the sludge generation. One example would be the freshwater sludge, which are generated in large amount in Singapore, and they can only be disposed by landfill. And also we have the requirement to carefully control the chemical dosages to avoid secondary pollution. Therefore, there's industry need to find alternative methods to reduce the chemical consumption in wastewater treatment industry. In SimTech, we focus on several technologies. One of the technology we are working on is the electrochemical advanced oxidation process, or in short, EAOP. EAOP, the principle of EAOP is use electricity to drive the generation of hydroxyl radical as a clean oxidant for organic pollutants removal. And depending on the features of anode materials, there are two kinds of hydroxyl radicals. They are the phase-sorbed hydroxyl radical and the chemi-sorbed hydroxyl radical, which can degrade organic pollutants in different mechanisms. And the two key factors for the success of EAOP includes firstly, the lifetime of the anodes, and the secondary, the catalytic performance of the anodes. And in SimTech, we have developed durable anode materials for EAOP applications, but I will not specify in my presentation today. And after anode materials, let's look at the hydroxyl radicals. As we know, hydroxyl radicals, they have many desirable properties compared with other oxidants. However, the main bottleneck for hydroxyl radicals is the short lifetime in water. And can we find a green and a sustainable way to tackle this problem? So our approach is through synergy with nanobubbles. Nanobubbles, they are very fine bubbles in water with diameters less than 200 nanometers. Because of this unique property, it can exist in water for quite a long time due to the Brownian motion. And because of the high inner pressure of nanobubble and the small size, the surface energy of nanobubbles could also be high. There's a report that nanobubbles could even facilitate the generation of hydroxyl radical. Because of this, there's great potential to hybrid EAOP and nanobubble for the long lifetime of hydroxyl radical. This slide shows some of the results for the synergistic effect of hybrid EAOP and nanobubbles. We are using the dye pollutant RHB as our target pollutants. We can see that EAOP alone could degrade the RHB to some extent. However, nanobubbles alone is not effective for the removal of this dye pollutant. But when we hybrid EAOP and the nanobubbles, we can see that there's a remarkable improvement in the color removal, which is almost total removal of color. And in terms of TOC removal, the removal rate also increased from 17% to 43% under the same experimental condition. And we have the EAOP for organic degradation and disinfection. Then a nanobubble could improve the oxidant activity, and also a nanobubble could remove some of the TSS by flotation. However, the residue suspended solids in water, we need to find an effective way to remove it. Therefore, our approach is to extending the hybrid approach to ceramic membrane for particulate rejection. So ceramic membrane could improve the performance by particulate rejection, and on the other hand, can EAOP and nanobubbles, this hybrid method, further improve the fouling control of ceramic membranes. With this, we built integrated wastewater treatment setup, which consists of 4 parts. The first part is the electrochemical cell, which could customize the electrode installation, and there's a nanobubble generator connected to the water tank. And for this setup, we have the ceramic membrane cross-flow to provide cross-flow filtration with a pore size less than 1 micron. And the other filtration unit is the micro metal sieve filtration, which has a bigger pore size, which is more than 3 micrometer. So by this design, this setup has 4 features. Firstly, it is configurable. We can customize the treatment process for varying receiving wastewater. Secondly, it can provide good removal for organic pollutants by hybrid EAOP and nanobubbles. Thirdly, because we have 2 filtration units, it can provide both particulate and micro filtration. And finally, we hope to achieve anti-fouling by nanobubble and EAOP without further chemical additives. Okay, so from this figure, we can see that when incorporating with nanobubbles, the membrane fouling improved in two aspects. Firstly, the membrane fouling was prevented at to a slower rate compared with the experiment without nanobubbles. Secondly, simply by a surface flush for 5 minutes with water and nanobubbles, we can see that the flux can be recovered to 77% of the initial flux, which is much better than surface flush with DI water only. So the experimental observation clearly indicates the advantage of this multi-physics approach. Then what is the mechanism behind? There are three proposed mechanisms. Firstly, the nanobubbles could inhibit the recombination of hydroxyl radicals. As we can see in the left, the nanobubbles lead to the supersaturated dissolved oxygen in the water. Even after even we power down the nanobubble generator, within 1 hour, there's no significant change of the supersaturated DO level. And as we can see from the reaction, the right side, the product is oxygen. So when the oxygen level is higher, we can inhibit the recombination of hydroxyl radical. And the second mechanism is that the high surface energy of nanobubbles could improve the lifetime of hydroxyl radical, which I have specified in a previous slide. And thirdly, because of the nanobubble, they have long lifetime in water, and they can also enhance the mass transfer of the system to improve the opportunity of reaction to improve the degradation of organic proteins. And it should be noted that by using air nanobubbles, we have achieved this result. And if we are using oxygen nanobubbles, we have the potential to push this even more. So for the future research plans, there are two ongoing or be planning. The first one is about the ELP, the electrode material development. We are looking to minimizing one of the bottleneck of ELP, which is the halogenated byproduct generation when the water have substantial halogenated elements such as chloride. And currently, this topic is supported by A-STAR grant. So we want to achieve this by both anode design and engineering the electrochemical cell. Then the second research plan is to scale up the current integrated wastewater treatment setup and make it digital ready in the future. So this includes the development of scalable and configurable modular, and also data analytics and predictive control by incorporating with sensors and IoT. So this is the last slide of my presentation today. If you are interested and want to know more details, please feel free to contact me. Thank you.
Thank you, Dr. Hu. Now we come to the Q&A segment, which would be moderated by Mr. Cedric Yon, Head Urban Sustainability Solution, A-STAR Enterprise. Over to you, Mr. Yon.
Thank you. Can you all see the slide? Okay. I only have one slide to show, which involves the summary of the modes of collaboration. Firstly, I would like to thank Vivian and Lily from Water Association for organizing this webinar together with SimTech and A-Star, as well as the three speakers previously for providing insights into their water sustainability technologies. So this slide is to summarize the different modes of collaboration with A-Star. But before we start that, we must firstly remember the goal of all R&D investment, which is for the success of Singapore industries domestically as well as internationally. So having this goal in mind, it helps us to navigate clearly in the muddy waters right now that COVID-19 has presented to us. So here I'll broadly share three categories of collaboration. Number one, technology development. So as you can see, there is this purpose. So what is the purpose of technology development? It is where technologies that are for technologies that are of mid-readiness level. So these are the technologies that are looking for domain adopters. So if you are the domain expert of certain industry, we welcome you to join us to further develop such technologies, as well as open for co-developmental efforts. So under this technology development, we have several modes of collaboration. For example, joint lab agreement, for example, research collaboration, which is one-on-one, and consortium collaborations, which we will bring in several stakeholders in the R&D value chain, as well as industry alignment projects. So this category presents a chance for companies to take part in the development process and co-owning the foreground intellectual property by their inventorship and contributions to the project. So often companies participate in this as they see potential disruption and synergistic integration of such technology into their products, thus value adding to their clients. So for the second column, which is technology translation, it is mainly for higher readiness level technologies. So often these are the technologies that require little to no customizations, and companies often license them off the shelf, be it as an end user license, or if you are a system integrator, you license it to provide such solutions to your customers. So under this technology translation category, we also have Innovation Factory, where it introduces design and engineering expertise in industry design and product design to catalyze also the innovation and scale up to production, as well as providing a co-working space for companies to do design prototyping. And lastly, we go to the third column, where we have the knowledge transfer and manpower development. The effect of technology development and technology translation is minimal without proper building up of competent manpower team to take over the baton. Thus, in this last column, in this knowledge transfer and manpower development column, we have training courses and academies for professionals, as well as a common program for our researchers to work full-time or part-time in the company to ensure that the technology is properly handed over and the team in the company is competent enough to take off with the technology. So additionally, we also provide technical consultancies for our industries via visits and outreach. So to sum up, we hope the industry continue to see R&D as one of the critical ways to value add and compete in this fast-paced environment due to technological advances. Yeah, so we will now open the floor to Q&A. As we can see that there are some questions already. There are some questions that are already on the floor. So, okay, Mr. Low Wah Sing actually asked a question to Dr. Dong, as well as Jasvinder actually asked a question to Weiyi. They are both answered. Are there any more Q&A questions that probably we could help in answering? You can just unmute yourself or type it inside the Q&A.
Maybe I can ask Derek's question verbally. So
Sure.
during the control experiment, do you precondition the wastewater sample to what pH? Yeah, actually, the wastewater for the setup we are using is all simulating wastewater. So we do not specifically precondition the pH. However, their starting pH should be the same. And in a future study, we can investigate this particular parameter to see what is the influence for membrane regeneration. Thank you.
Thanks. As well as for Cadence, are there any fees applicable for the Green Compass Plan, and how do we engage for this initiative?
Right now we are in the validation phase, so we are inviting companies to help us in our validation journey. Subsequently, we are hoping to run this together with as a course, so that companies, in addition to doing the basic assessment, they can also develop sustainability improvement competency that can bring them beyond just doing the basic assessment.
Thank you. Are there any other questions?
Some additional points related to Mr. Lowe's question, the service lifespan of the ceramic membrane. Our ceramic membrane can withstand a temperature up to 600 degrees. That means you can bake these ceramic membranes when there are fouling issues. Most of the contaminants are organic, so they can be burned off and regenerate this membrane at a 500 to 600 condition. So this process would enable all the end users to reuse, recycle, and regenerate their ceramic membrane module. And for example, we have been using our first batch of membranes for 3 years over our research project. And the fallout are usually the organic dye and other content residue. And overall, the membrane after the burning or say thermal regeneration, we don't see any leakage or gas permeation. And this is the unique advantage of our ceramic membrane versus the non-recyclable polymeric materials.
Okay, if there's no other questions, I think I will take over Cedric.
There's one question
One
about
more question?
EAOP.
Okay.
Yeah, maybe I address this
Okay,
first.
thank you.
So what is the largest scale have used for EAOP? For now, the EAOP, the electrode we have has the dimension or the surface area of about 50 cm square. So we tried it for the large scale. The treatment capacity is below 2 liter, together with the nano bubbles, and we can because EAOP is a technology that could be scalable easily. In the future for system level, it could be easily scalable. So this is my answer. Thank you.
Okay, if there's no other questions, then Lily, you want to take over?
Okay. Okay. Once again, thank you all and the speakers, and we look forward for all to attend our upcoming webinar.
Thank you, Lily.
Thank you, everyone.